Chapter 4 demo, problem number 1. So let's open this in StatCrunch. Let me share that video, that screen with you. We can go ahead and close this. Okay, so chapter 4 involves analysis when you're dealing with two variables to see if there's an association or somehow related. In chapters 2 and 3, we were just dealing with one variable, but sometimes we want to see if two variables are associated, like is exercise and the number of hours you sleep associated. So they can do a study. Let's say this, I'm going to put context to this problem because they're just saying two variables, but they're not telling us what it is. But it makes more sense if we talk about it in context. So I'm just making this up. So the numbers might not make complete sense, but let's say X represented the amount of hours exercised, and then the Y represents the number of uninterrupted sleep hours. So maybe these are just patients that were surveyed because they suffer from sleep apnea, and they want to see if exercise is associated with more uninterrupted sleep for patients who suffer from insomnia, let's say. So for example, this person who exercised 7 hours, let's say in one day, maybe they just walked and they were in a marathon or something, who knows. They slept for 3 uninterrupted hours. However, this person who exercised 1 hour was able to sleep 6 hours of uninterrupted. And that might be a lot for that person since maybe they normally sleep 3 hours or what have you. So we want to see if there's an association between those two. So the first thing we do is just like with regular quantitative and categorical data, we make graphs. We see a visual graphical representation of the data. So that's the first question. So we're going to go to a graph, and these graphs are called scatter plots. So select scatter plot. In this case, the X column is labeled X and the Y column is labeled Y. However, sometimes if they did not tell us this, like if this was real research, you would have to determine what the input variable would be, which goes on the X axis, and what the output variable would be, which is the Y value. So usually we put the independent variable on the X axis and the dependent variable on the Y axis. So for example, in this case, if this was exercise hours and then hours of sleep, then we would say that the sleep hours depends on how many hours you exercise. So we put the hours of exercise here, and then as a result, how many hours of sleep you got. So we wouldn't do like put the sleep hours here. We wouldn't first say, okay, how many hours did you sleep? And then we would say, okay, then that means that's going to determine how many hours you exercised. So would it make sense to put them in the opposite direction? Okay, so then just check which diagram matches yours. They're all, different, so there should only be one clear response here. Compute the correlation coefficient. Let me close this. The correlation coefficient, called R, is a numerical way of measuring the strength of this relationship. So maybe there's not a strong relationship between the number of hours you exercise and the number of hours you sleep for, insomnia patients. Maybe there's no correlation. Maybe for a regular person there is, but maybe for insomnia patients there isn't. So that we need to know that maybe there is an association. Visually, we can see that there's something going on, but maybe that association isn't strong enough, or it's a weak association. So it's a way to measure how strong these two variables are associated with each other. The values of R that R can take on vary from -1 to +1. +1 being a very strong relationship, close to 0 being no relationship or 0 relationship. And on the other end, on the negative side, -1 is also a strong relationship. We just say it's a negative it's a strong negative association. And that just means that the trend of the, instead of the trend of the dots going up, the trend of the dots go down. So there's a strong relationship, but it looks like it's a negative association instead of a positive association. So let's compute that. So that would be in a different place than StatCrunch. In fact, I don't even use this scatter plot. You can actually get everything from the statistical analysis of regression analysis. So you go to stat, regression, linear. Now there could be like sometimes the pattern or the trends might be what we call curvilinear. So we might have other analysis we can do. But in this class, we're just going to simplify things and just do associations where the trend or the pattern seems to be of linear fashion. So simple linear, so simple linear regression. But the option just said regression, it didn't say linear regression. So X, Y, and then just compute. It's going to be a lot of information here. We just have to kind of sort through what we need and what we don't need. This little arrow here, because it says page 1 of 2, if we select it, gives us, again, the scatter plot. So that's why we don't really need to select that option, because if we do the actual regression that we're going to have to do anyways, it kind of gives us the diagram. The only additional part here is that if StatCrunch is going to assume you want an association, so it's going to draw like what we call the best fit line that goes through the middle of the data to the best of our analysis here. There's some calculations that decide what we consider the best fit line, which is the one that goes exactly through the middle of the data. We won't have to worry about how that's determined. We just need to know how to use it. So going back to page 1, the R, here they use a capital R instead of a lowercase r, is negative. Now the reason it was negative is because see how the slope of the line is, it's kind of going down from left to right, it's decreasing, so that's a negative association. They want us to round it to 3 decimal places. So the first 3 numbers after the decimal. And then again, you have to look at that 4th digit to see if you should make that last digit stay or if you have to increase it by 1 or round it up by 1, which in my case, I do. Now my association was negative, so you have to make sure you put that negative sign in there to show that the association is decreasing. And now it's the interpretation, how it's 0.1, that's pretty close to 0. So, I mean, you could see that these points are not like showing a very strong linear association. Here's the equation of the line, y equals mx plus b, but in this case, they're doing b plus mx. They switch it in statistics because they like to show the y-intercept first and then like the slope that describes the pattern, the linear equation that is drawn. They're telling you which one's the dependent, the independent variable. They're telling you how big the sample size is. They're squaring R for some other purposes, and this is how much error based on the way this line was drawn that you can expect. So you can, if you want to, the whole point of using this, getting an equation is to make predictions. So if there is an association, we can just say, okay, if a person exercises X amount of hours, we can use this model to predict how many hours of sleep this patient will get. But we can be off by give or take 2.5 hours. Now that's a huge error. Why? Because the association was low. So it's not a useful model because if you're going to be making predictions and you can be off by up to almost 3 hours, then what's the point? So then at that point, the researcher would say, oh, that, we either have to get a larger data set or there was no association. So why use the model to make predictions if those two weren't associated to begin with? Okay, so now that we know the R value, we're going to, because we have a small sample size, we're going to compare it to some standard. And that's called, the table is called the critical values table. Not all, sometimes occasionally the book doesn't give you, the StatCrunch doesn't give you this table. So what I've done is I put this table on Canvas, and it's called critical values for a correlation coefficient. It's on the home page. So you can look it up there if for some reason, I don't know, it's not handy. So we're going to look for our sample size here, which was 5. And it's the value of given is 0.878. Let me write it over here because I'm going to close that. So for n equals 5, the correlation the critical value, I'm going to use CV. Sometimes you'll see that in the notes. Critical value is 0.878, 0.878 for a sample size of 5 here. This one here. So if your sample size is 11, you would put 602. So what this critical value is, that how do we know this association is strong enough? When we compare it to this table, our correlation coefficient, our value that measures the strength of this particular data, has to be higher than this cutoff for there to be a strong enough association for us to be able to use this equation to make predictions. So I'm gonna close this. Now ours is 0.112. Well, and we're not going to look at the negative. We're just looking at the number itself, just to measure the strength. The negative is just saying we have a downward slope instead of an upward slope. So that has no bearing on the actual measurement of our the 0.1112. So for us, with a sample size of 5, we would have had to have been at least an R value of 0.878 for us to say, okay, there is some association, something's going on here. We can make this, we can use this equation to make predictions, or we can show that, yeah, exercising is associated with the number of uninterrupted hours that a student who suffers from, a person who suffers from insomnia will get. So because ours didn't meet this criteria, we cannot do any further analysis. Okay, so let's see how we're going to put that into words. Because the correlation coefficient is, in my case, it was negative, but if yours is positive, then you put positive. And the absolute value of this value, because again, to do this analysis, I don't really care whether it's negative or positive. We're really just analyzing the positive value here. So if yours was positive here, like let's say you had a positive 0.1112, then you put positive, and then you're still going to put a positive 1.12. So we're just looking at the actual numerical measurement of that strength, not the sign. The sign just indicates direction. So that's why they're saying the absolute value, just to remind us, like, no, we don't really care about the sign here. That's not going to determine the strength. We're just concerned about the actual value that has to exceed this cutoff. So because this number, which happened to be negative, but the absolute value is 0.1112, is not more than, not greater, or greater. So depending on, mine was not greater than the critical value. So my 0.11 was not bigger than the critical value of 0.878. But if yours is, then you'll say, yes, it is greater than the critical value for this data set, comma, and then put the critical value in here, 0.878. Then you say there is or there is no association. So for me, no, because it didn't meet the criteria. But if yours was yes, then you would say, yes, there is some association. And then you could say whether your association had been positive or whether your association had been negative. So, but in my case, it was no. But if you said it was greater, then if this is positive, you'll say there's some positive association. If it's negative, you'll say there's some negative association, depending on the trend. But had there been an association, I would have said, yes, there's a negative linear association. But in my case, there wasn't. Okay, question 2. I'm going to close this tab because I don't want a lot of tabs open. Move this to the left. I'm going to open this in StatCrunch and share that with you. So go ahead and open your data in StatCrunch. So what I like about this one is now that they're putting it in context. I'm going to go close to this column here. So like until I see a little like double arrow, just to kind of make it wider. I just kind of want to see those titles. You don't have to, but I like to see like the full title here, which is matches what was on StatCrunch. But so these are the titles, so you don't have to do that. The data in the table to the right are based on results of a survey comparing the commute time of adults to their score on a well-being test. Compare parts A through D below. Click on the icon to view the table of critical values. Again, that's later. We'll click on here to compare it to the cutoff to see if there's a strong enough association. Okay, so it's commute time and then some score that describes their mental well-being. So there's trying to see if there's an association between commute time which the lower the commute time, maybe the higher the well-being score, or like people who have a high commute time or a long commute time, maybe their well-being score is lower. So we'll see if those two are associated. We hear about those type of surveys all the time. Okay, so in this case, which one is likely to be the explanatory and which one's the response? So the explanatory is the one that goes on the horizontal axis, and as a result, the dependent variable is on the vertical. So we can say, okay, does the commute time, how long you drive, depend on your well-being? So if I'm like a happy person, is my commute time going to depend? Oh, because I'm a happy person, my commute time depends on that. No, the commute time depends on how far most likely you work, right? So then it's the other way around. Your well-being, your mental state depends on how long you're on the road for. Okay. So because the well-being depends on how long you're on the road for, then the commute time is the independent one. And then the well-being, your well-being depends on that. So because this is the independent one, which is what you would probably record first, that's on the horizontal axis. And as a result, then on the y-axis, it's the dependent one, which is the well-being. So let's see which one that is. The explanatory is the commute time, and there's two that say that. And then the response is the well-being score. There's two that say that. And then it's the because well-being score affects the commute time, or is it because the commute time affects the well-being? Okay, so choose the appropriate one. But think about it, make sure it makes sense in your mind, like why we chose that. Okay, so now we're going to draw the scatter diagram. So I'm not going to go to the graph. I'm going to go straight to the regression analysis because that'll give us both. So regression, we're only going to select simple linear. Choose your X. Now, just as a little clue here, usually StatCrunch will put the X first and then the Y second. So if you're not sure, this one is the X, the commute time. They'll put it in order for us, which helps us out in identifying which one's the X and which one's the Y. But you know, in the field, you would have to make that decision. It's kind of how we talked about it. So we usually don't worry about anything else for linear regression. We just compute. Move this over slightly. Then I'm going to click on the right arrow to see like the trend. So in this case, you could see there was a stronger association compared to that first example we have, even though there still isn't a lot of measurements that were taken. It's not enough to do a true analysis, but even with these, you know, let's see how many people were there. 7 people, you could see there's some type of a trend. Again, it's decreasing. So it does seem like to be an association, but a negative association. So just pick the one that shows. So for me, it'd be between these two. This one goes to 70 and this one goes to like close in the hundreds. So if I look here, it looks like it's close to 70. Well, by process of elimination. The only negative of this is that this one does starts at 0, but this one doesn't. This one up here didn't. Oh, wait a minute, it did. I thought for some reason it didn't. Oh, this one does it. This one starts at 60. I knew I had seen something like that. So that's not good to start at 60, right? That's not a good graph. So ours starts at 0. And so we want to choose from the two that start at 0. Now let's determine that R value. So now we can go to the first page and look for the correlation coefficient, the strength of this association. See how it's really close to 1? It's a really strong association. The negative is just saying that it's decreasing in the negative direction. Okay, to 3 decimal places. And then look at that 4th decimal to decide if you're going to round it up or keep it. My next digit is greater than a 5, so I'm going to round up. Now, I don't need to compare it to the table to know that there's an association, but let's check it against the table. Usually anything above 0.7 is going to be really good. But our sample size is small, so it's good to kind of compare it. So click on the icon to see what the cutoff is for us to conclude that there is an association between commute time and well-being. Okay, so just the sample size is 7. So this time we have to look at the row 7. And this time we would have had to exceed 0.75 or 4. That's the cutoff that we have to exceed to say that there's an association between these two variables. So let me put it down here because sometimes they ask for it. So that's the critical value equals 0.754 before I close this. Or if you have a good memory, you can keep it there. Okay, so let's say, does a linear relationship exist? Well, my R value was 0.989 and this is 7. So yes, mine was higher. So yes, there is an association. So I look at all the answers that say yes. Ooh, there's a lot of options here. So be careful, read through all the options because sometimes like the difference of the statement is really close. You might have the right idea, but you choose the wrong option. Yes, the variables commute time and well-being are negatively associated. For me, yes, because it was negative. So if yours is positive, you're going to look for those statement that says positive. So yes, that's true. See how this one says, yes, they're positively associated. For in my case, it's not. So I would not choose that one. And then option D also says that it's negatively associated. So that might be an option. And then option F says that they're positively associated. So no. So I could start eliminating options. So it could be A because it's a yes with negative association, or it could be D because that one's also a yes with a negative association. And then it says because R is negative here, and then this one says because R is negative, positive. No, my R was negative. So by default, then that's the one that's stating it correct. And the absolute value of that correlation coefficient is greater than the critical value. So see how they want the critical value here? So that's where I would put that. So the absolute value of this number, which is 0.988, would be greater than 0.754. At any time, again, feel free to pause the video if you need to catch up. Okay, so the next example, open it in StatCrunch. Let me share that video with you. I mean that screen with you. And we can close this. Notice here, there's also telling us what the X is and what the Y is. Or if I make these wider, they should also be labeled here. A little bit wider. You don't have to, but I just want to see the whole thing. It's nice to know what things are being measured in. A pediatrician wishes to determine the relationship that exists between a child's height and a head circumference. So is, as the child gets taller, which means older, does their head circumference also get, I'm assuming, greater, right? Greater, or does head circumference not related to the child's height? I mean, it would make sense. Now for adults, we might think like, oh, the taller the person, let's say the longer their foot size. And it turns out that there is no association between foot length and height. So not everything in terms of the body measurements would be associated. So you could have like a fairly shorter stature person, have a bigger foot size and vice versa. Okay, so let's analyze this one though. She randomly selects 11 children from her practice, measures the heights and the head circumferences, and obtains this data. So here's the data for the 11 children where she recorded their height in inches, and then their head circumference in inches as well. Find the least regression line. Okay, so now we're saying there is an association. So we're going to assume she checked that and saw that there was a relationship, an association, a strong enough association where we can now use it to make predictions of maybe what the head circumference should be for particular children of certain heights. That would be useful, like if we would want to know if a child's head is not growing appropriately compared to what it should be. So, we can see if we have unusual measurements and then, obviously do further testing on those children and seeing why they're not growing appropriately and so forth. Okay, so stat, regression, we're only doing linear, click or select, and then come the height. Now why was the way she put it was, she was saying that the head circumference depends on the height, because that's the output, the independent one. The height is the independent one. In terms of they labeled it for us, but I guess technically you could have said that you could also use head circumference to predict the height. You could do the other direction. But the way it's set up, we're going to say that the head circumference depends on the height, which would be the more typical direction we would take. Okay, so the 11 children. Let's get a visual for that. So there does, I mean, it doesn't look like, they're tight. Those dots are not tight, but there does seem in general a trend that looks like it's getting higher. Those dots are getting higher as the height increases. So the trend seems to be that as the height is increasing, the head circumference is also increasing. Is that a super strong association? Well, it's not like a 0.999, right? But let's see how it's a little bit weaker than that previous one. It's like a 0.8. But in research, 0.8 is considered extremely reliable and strongly associated, where we can use it to make predictions. Okay, so now they want the equation. So because we used y and x here, it shows up as y and x, but sometimes it'll just show up as like the head circumference equals this plus this times the height, like they do here, but then they put the x there. So it's kind of, they're trying to put it in context, but we want to put the number that's next to the x first and see how here it's second. So you have to be careful because in StatCrunch, it's like b plus mx, but here they're putting mx plus b in terms of like the general equation. So 3 decimal places. So the number next to the x is what we call the slope. So it's this one. Again, don't forget to round. We want the slope to 3 decimal places. If you're not sure, there's a hint over here. See how this one says slope? So you can go down here and look for it. It'll be more clear so that you don't make a mistake here. I'll have to round mine up, so I just forgot to do that. And then the constant, which would be the y-intercept. So here they're just calling it the constant, the number that's just by itself. You'd have to know that that's intercept over here, or you could look here that it's the number by itself is over here. So, but it appears here again to 1 decimal place. So just one number behind the decimal. Now mine's kind of tricky because it's a 12.9 and the next number is 8. So if I bump up that 0.9 by 1, and then it becomes 13.0. So we'll assume that they already did the analysis to show that there is a correlation so that we can make a prediction. These type of problems are hard to analyze. Like, how do we interpret the slope and y-intercept in context, like of the meaning here? So the slope is how fast this line is, the rate of increase here. How fast is it going up by as we increase the height by 1 inch? What's that rate of change? So the slope describes that. So if I make a fraction out of this slope, 0.176 divided by 1, that means that's how fast it's rising for every additional inch. So that describes how fast this is increasing, the y is going up by, for every one of these. For every 1 additional inch in height, the head circumference is growing by an additional 0.176. So this here represents the y variable, how fast the y variable is going up by, at what rate. For every one of these, which is for every inch, additional inch in height. So for every inch in the head circumference, no, it's for every inch in height, that's how fast the circumference is increasing up. So that would be that. It's a rate of change. These that involve 0 are for the y-intercept. Like this here is kind of bad because it doesn't give us like the 0 here. So unfortunately, because it's just kind of showing the window of like where the data was found. So they don't want to show like between 24 and lower, because these models, they can only be used like if I want to make a prediction on a child for the span of measurements that were taken. So like, for example, here it looks like there was one at 24 and one at 28. So if I want to use the model to predict somebody else's head circumference or another child's, I could only do it for children that are between 24 and 28 inches tall. Like I can't do it for, let's say, a 4-year-old, 5-year-old or 6-year-old. So what we say is we can only make predictions within the scope of the data. So if there was a child that was 29 inches tall or 23 inches tall, we wouldn't be able to use this model. Why? Because I don't know if the trend would continue. What if all of a sudden it drops or there's a curvy linear relationship? So the model is only as good as the spread of the data of the measurements that were taken. Okay, so for every inch increase in height, the circumference of the head increases by 0.176 for mine. You would put yours inches on average. So again, this 0 is for the x-intercept, the y-intercept, which is not being shown here. So it's kind of hard to see that because it's not drawn. But that's the next thing. Interpret the y-intercept if appropriate. Well, the fact that no measurements were taken on for when x was equal to 0, that's where the y, if this is extended, then it's going to cross the y-axis eventually, and this is saying that's going to cross it at 12. Where's my equation? Around 13 if I rounded it. It should cross around 13 if I were to. It's not drawn to scale, but because of the 0 here. So, but if I were to extend it on a normal axis, it would cross at 13. But this is deceiving, so don't base it on that because it's a bad graph. But it's beyond the scope of the data. That's why it's not even shown. So it wouldn't mean we wouldn't be able to use it. So it's not appropriate to interpret here, basically. That's why I say if it's not appropriate. Well, and then it makes sense, right? You're not going to have a child of height 0. So when you're doing the y-intercept, it's where it's crossing the y-axis. It's when x is equal to 0. So all the interpretations of y-intercept is when that x is 0, what's the y? Well, when x is 0, the y would be 13. But then that would mean that when a child is 0 inches tall, their head circumference is going to be 13, which makes no sense. So because it's beyond the scope of the data that was collected. So it wouldn't make sense to interpret that, even if we wanted to. But sometimes could be an interpretation where there's 0. Let's say if a seedling of a tree is planted as a seedling, then at time 0, the height is 0. And that would make sense. Okay, now we're going to use this to make a prediction. Okay, so let's say, okay, let's use it. Let's use the model to predict the head circumference of a child who's 25 inches tall. It is within the scope of the data. In fact, there was an actual child that was modeled, but just in general, we can use this equation to see what the model is predicting this value. So there is kind of like some error here because this is what happened in real life. It was like around 17.2. But if you were to use the model, it's going to say that the height of the child should be here. And in fact, if you did measure another 25-inch tall child, the measurement might be different. Here's 2 children that were measured at 26 inches and their head circumference was different. It could be a male versus a female. Even if it was 2 males or 2 females, there's going to be variation because just genetics and things like that. So from sample to sample, it's going to vary anyways. But here's what the model's predicting based on all the data that was collected. So let's see what the model predicts. So we're going to go to options, edit. And like I said, a lot of stuff is nice here because then StatCrunch does it for us. So if you go down, if you scroll down, here's when you want to make predictions. We could technically do it by hand. We could do for a child who's 25 inches tall, we could put a 25 here, multiply it by this number, get that answer and add 13, and then we'll get the prediction of the head circumference. But we could have StatCrunch do that, perform that operation, so we don't have to do that. Okay, so we want to predict, in my case, for a child who's 25 inches tall. So I'm going to put 25 here. So if yours says 30, yours says 26, if yours says 24, 23, just put that there. And that's the only thing we have to do. You can ignore all this extra stuff. Compute. It's just for further analysis, more in depth, which we're not going to be going through that. And then you could either make this little window bigger so until you see the bottom of this, or you can scroll down here, just scroll it up here. So here's the section for predicted values. So when I put it in 25-inch tall child, the model is predicting that the head circumference of this child would be 17 point something. 2 decimal places is what they're asking for. And then just make sure you check that next digit to see if you're gonna have to round up. Okay, so now we're gonna say, okay, we know that we risk of having some error. This confidence interval, which we're gonna do in the future, just says that, okay, maybe it's not gonna be 17.3 because we know there's gonna be variation from child to child, but we're pretty confident that it'll be somewhere between 17.294 and 17.52. I don't know, that child was 17.2, so it's a little bit below that actual measurement. But it's in the ballpark of these two is what we're saying. All right, so the next is compute the residual based on the observed 25-inch tall table child in the table. Okay, so now I'm gonna close this so I can see the original data. Okay, so now look for your child's height here. Mine happens to be 25 and yours may be as well. I'm gonna click on it so I can highlight it. So for a 25-inch tall child that was actually measured, their head circumference was 17.2. The residual is like how much were you off by when you actually measured the child versus what the model predicted. Okay, so the model predicted 17.38. What? There's no calculator here. Okay, so let me pull up my computer calculator. So just pull up your calculator and do that. So I'll just do this really quick. Okay, so mine happens to be a negative 0.18, but you compute yours. So the residual, this observation was negative for mine. Well, because when we looked at the diagram, so you're going to take the actual measurement, what was observed, subtract the predicted one. In that order, you can't put it in the other order. So, because then the negative will indicate that the measurement was either above or below the negative means that the measurement was below what was predicted. If you get a positive, that means the real life measurement was above what the model was predicting. So because mine came out to be negative, it means that the head circumference of this child, of this particular measurement, was below the one that was predicted by the regression model. So let's look back at that. So I'm going to go back to StatCrunch, my previous results. This one, let me look to the picture here again. So here's the one that is in pink. The true measurement was below than what was predicted. And that's why it came out to be negative. That negative is indicating that. But again, you have to make sure that it's in the order, the observed minus the predicted, to get the correct positive or negative answer. Draw the least square. So now I'm going to go back here in my previous results. Select it again. And here's the diagram. It's on the page 2. So again, just kind of look for the one that's the correct trend. So you might have to pop these up because the residual is a little bit tricky here, but because they all have the same shape. But now this one is not correct because the line is horizontal. So here's my vertical lines here. So I see this dot here, and then I have one dot that's on the line and then one's above. The first 3 dots, see how the first one's above and then these 2 are below. So that can't be it. One's above, okay, these 2 are below. One's above, these 2 are below. And then I have this one that's below, these 2 that are below here, where this one seems like on the line. So it looks like it's this one. If you could also see that, let me pop it out because it's 0.18 there. it's really hard to look at the distance here. This should be 0.18. This one. So let me just verify that. But the way they scale this is kind of hard. So if this goes from 16 to 18, then halfway is, this is 17. And that's 5 boxes to get to 17. So if I divide, if the difference between 16 and 17 is 1, and I divide it evenly to 5 boxes, that's 0.2. Each box is 0.2. So this distance here is 0.2. Ours was 0.18, which is close to 0.2. So that kind of verifies that that little length is correct, whereas here, it's probably like less than 0.2, and then here's like almost right on it for that. The residual is for this point here, the one that's 25. So that one's right on it. There's 2 that are below, and we know that was 2 that was below, but ours was a little bit more significant than that distance. But we can base it on the placement of the dots, so we don't have to analyze that. Notice that there's 2 children that are 26 inches tall. Let's see if that's true. Let me clear. Um, 26. So I see one. Yeah, here, these 2. One has a head circumference of 17.5, and the other one has a 17.7. Yours might be different, so just kind of read along and follow your example. So how could this be? So kind of read it first, think about it, pause it, see if you can pick the correct solution, but don't check answer. And then continue the video and see if you got it correct. Okay, so there is no logical explanation. No, there is some logical explanation. So hold on a second. The only explanation is caused that they measured incorrectly? No. The only explanation is that the difference is due to the fact that one was a boy and girl. We don't know that. They never told us. Okay, so you should have thought of selecting D. For children of height 26, the circumferences of measurements are going to vary just by genetics, for one thing, diet for another, in terms of what's going to determine the growth of that child, so forth. Would it be reasonable to use this least squares regression to predict the head circumference of a child who was 32 inches tall? Again, think about it before I go over it. I'm going to go back to the diagram to illustrate why we're going to choose the answer we're going to choose. So here's my diagram. Let's see. Okay, so for 32, okay, here's the smallest was 24 and then goes to 28. 32 is not within that scope, so we are not allowed to make predictions for children who are above the 28 or below the 24. So no, not that this height is possible. No, because the height is outside of the scope of the model. So we are restricted into where this equation to make predictions for other children would apply. Okay, so here's another example on linear regression analysis. So let's open this in StatCrunch. And, the car weight and MPG, which represents miles per gallon. So the weight of the car and then the miles per gallon that you're going to be able to travel on each gallon of gas. And they're telling us again, which one's the X, which one's the Y. So they help us out on that. And expand this just so you can see the complete title. Find the least squares regression line treating weight as the explanatory and miles per gallon as a response. So they're saying that because the miles per gallon is the response, we're saying that the miles per gallon that you're going to get depends on the weight of the car. So that's the decision. So they've already done the analysis. They're saying that there is an association, so we can use this model to make predictions for other weights of cars as long as it's within the scope of these weights. Okay, so again, we go to stat, regression, simple linear. Choose your X variable, which is labeled as X. Choose your Y variable, which is labeled as Y. Compute. So there's no like guessing as to which one's the X, which one's the Y. I'm going to look at the diagram first, because as a statistician, that's what you would want to do. Just get a visual to see if visually there seems to be some association or a trend. And there does seem to be a trend. It seems like as the weight of the car increases, the trend seems to go down. So it seems to say that you're getting less miles per gallon, which would make sense, right? The bigger SUV type cars and big trucks, you know, they tend to get less miles per gallon than the small compact economy cars, let's say. So, you know, the behavior makes sense as to what is being depicted here. We call this a negative association because as we move from left to right, the slope is negative. Now, how strong is that association? They have determined that it's strong enough to be able to use this as a model and to say, yes, they are connected. Okay, so let's go back to diagram 1. Let's look for our equation, which is here, which is again going to be backwards, right? So like the number next to the X is this one, that's the slope. So and number next to the X actually comes first over here, and they want the X to 5 decimal places. Always read how many decimal places you have to round this off to. So here they said the X coefficient. They didn't say the word slope like in the previous example. So you have to be careful. The one that's next to the X is the weight, which is the explanatory variable. So it's also going to be what was on the x-axis. So the slope, 5 decimal. So 1, 2, 3, 4, 5. So the first 5 numbers after the decimal, including negative, because that will indicate the direction of that line. And then just check to that next number to see if you're going to have to bump that up or that 3 or not. In my case, no. And then the constant to 1 decimal place. So the constant is the y-intercept. The constant is a number that's by itself. So it's 38 point something, rounded. So we can use this model to make predictions of how many miles per gallon we're going to get for other vehicles, as long as they're within this scope of measurement. So it looks like somewhere in the low 2600s, not exactly 2600, it's a little bit more. We could look on the table of original values to do that. And then maybe a little bit more than 3,800. So we'd kind of have to look at the, if we were interested in the actual cutoff, we would have to look at the values here and see which one's the smallest and which one's the largest. And that would limit us on the left end and on the greater end. Or we could sort these, but I wouldn't sort it because then you would mess up the number that goes with this one. So don't do that. Okay, so now we have to do the interpretation, which again is a difficult to meaning behind here. So the slope is like, how fast is this line decreasing at? What rate is this line decreasing at? For every additional pound in the car, that explains how fast that Y is changing, how many miles per gallon less you're going to get for every additional pound. So for every pound added to the weight of the car, yes. For every pound added to the weight of the car, yes. Okay, so that's, you can always interpret the slope. It's the y-intercept that you may or may not be able to interpret. A weightless car, so if a car weighs 0 pounds, that doesn't even make sense. But that's interpreting the y-intercept, like if the x is 0, if the weight is 0, which is beyond the scope of the data. Anyways, it wouldn't be appropriate to interpret there. So for every pound that you add, that's how fast the y is changing. It's going down. So let's see. For every pound will decrease. Okay, they both say that by some amount on average. Okay, a weightless car will get blank miles per average. And it's not appropriate to interpret the y's. That's true. It's not appropriate to interpret the y-intercept. A weightless car, that means if a car weighs 0, no, we're not interpreting that. So it looks like this one's the one that best fits. For every pound added to the weight of a car, your gas mileage is going to go down by the slope. Use the answer from part A. Okay, so I guess they want us to use this entire number here. So it's going to decrease by, you're not going to put the negative here because of the word decrease. It's already assuming it's going down. So it's going to go down by this amount. So don't put the negative because of the word decrease is always is already indicating direction on average. And then we're not going to interpret the y-intercept in this case because it's beyond the scope of the data. Plus it wouldn't make sense. Why? Because it's beyond the scope of the data. A certain gas-powered car weighs 3693. Okay, it's 3693. It might be out of the scope of the data. Let's see, 36. Oh no, there's one that's 38. So we're okay. All right. These I was looking over here. 36 something is in here. Yeah, that's good because it's 3800 is still on there. So yeah, we're within the scope of the data. So we can make a prediction. So a certain gas-powered car weighs this many pounds and gets 20 miles per gallon. So there was some measurement that was taken. Is the miles per gallon of this car above average or below average for cars of this weight? So we can use this as our average. So this is like the middle of the data that was collected. So on average for a 3693 car, this is what the model's predicting. So somebody measured a car. Let's see if the model predicted something that was close to that. So let's go to the first page and make a prediction to see what the model would predict. So go to options, edit. We'll scroll down to the prediction. So we're going to make a prediction for a 3693 pound car, but make sure you guys always use your values. Don't use mine because you'll get the wrong answer. Okay. The actual measurement was that this particular vehicle got 20 miles per gallon. Let's see what the model predicts. Compute. Scroll down here till I see the predicted. Okay, so this, we went 3 decimal places. This is what the model is predicting, that you're going to get about 18 miles per gallon. The miles per gallon of this car is above or below average for cars this weight. So the 3693 for a car that weighs 3,693 pounds, the actual measurement was 20, but the 18 the 20, I'm looking at the wording here. The miles per gallon of this car, so of this 20 miles per car is higher than what the average for cars of this weight is. Because sometimes they could word it like on the opposite direction. So just be careful of the order of the sentence. So for this car, 20 is higher than what the model was predicting the average. So the average that the model predicts is about 18 on average. This car actually was 20. So this car was above what was average. So this car's getting a little bit more than what the average is expected to be. Last part, would it be reasonable to use the this regression line to predict the miles per gallon on a hybrid gas and electric car? Well, these were just domestic cars and miles per gallon. At no point did they say these were measurements on hybrid. So that's kind of like the same idea as beyond the scope. You would have to do a different type of test to include hybrid cars in your models, because these are for like just regular cars. We're not doing any particular like electrical cars, hybrids. So we would have to do a complete analysis. So is it reasonable? No, there's 2. Because the absolute value of the correlation coefficient is less than the critical value. No, we were already assuming that that was checked and that the strength, the association was strong enough so that we were able to make these measurements. So that was done already. We were already assuming that. So that has nothing to do with this. No, because the hybrid and the electric car is different type of car, correct. Okay, so that concludes chapter 4 demo. There is no chapter 5 demo because chapter 5 is mainly on like the odds and chances of something happening, probabilities. So the next recording would be for chapter 6.